All right, any questions? Starting late again. Project questions? Yeah, we're going to go over that today. All right. So let's talk, and I want to not just say, here's the topology. I want you to understand what's going on. And so I'm going to give you an example of a project, all right? And then we're going to go from there. I'm going to step you through because you know all the fundamentals now. We just need to apply them, okay? So, we start out, I'm going to just do a diff amp. And let's talk briefly about the diff amp. When I draw this, does anybody cringe and go, I don't know where bias goes? Okay? I don't know how to calculate the op-amp's minimum input common mode range or maximum input common mode range. Does everybody understand? Everybody understands. We went over why in an op-amp the two inputs have to be at the same voltage, basically. I mean, they may be off by a millivolt or whatever, but they're basically at the same voltage. And if that's the case, what can I say about the current that flows through each? The same. So this voltage here for DC biasing is the same as this voltage because they have the same VSG and the same currents, right? Now the gain here is hundreds, but ideally for an op-amp I have really high gains. So I'm going to add a second stage to this that's a common source stage. Now this node I think of as being tied to the gate drain connected, which mirrors the current that flows down here. We'll put times 2 so that we have 2 of them. We could split this apart, right? Now I'm going to put another current source here and connect this to the same V bias. Let's just do it like that. And then I could call this the output of the op-amp. This would be node 1 in our compensation scheme. This would be node 2, and we're going to talk about the compensation capacitor we're going to add here. Compensation capacitor kills the gain at high frequencies to keep the op-amp stable. However, your projects, if I remember, have to be able to drive a resistive load, right? So what I'm going to do is I'm going to add a source follower on the output as a buffer. So this is a diff amp. This is a gain stage. And then I'm going to put a buffer, which has a gain of 1. And I'm going to, notice this is the output. This is an NMOS. Does everybody see that? Okay, and so this is V out of the op amp. Looking good? So I'm gonna go through and do sims now, and we're gonna look at this, and then we're gonna just play around, and then we're gonna go into the theory of the design. But I want you to feel comfortable that you actually can do something with what you know, because my feeling is you're like, well, I've learned all this crap, but I can't do anything, and you actually can. All right, because we have all the fundamentals. Question?
Just curious for the actual. You know, you probably answered what you're saying. So
all right. So. I don't know how to select C sub C. I don't know how to select the sizes here. So I'm going to use the values from table 9.1 as a starting point. Now notice, you're not doing your project using the process, the 1 micron process. You're doing it using C5 process. Okay? So you have to go through and get the VGSs and all that other stuff. All right, any questions? Yes?
Just clarity, that's 2x2, you mean another NMOS
This one?
parallel to, no,
This means 2 in parallel, twice the width, m equal 2. So I could draw it as 2 separate ones, or I could draw it as m equal 2.
So bias 4 goes to connect to that, and bias 3 connects to the other.
No, bias 4, if I'm using, connects to all of them. Is?
So with the C5 process, can we use the 500 or the 500 nanometer, like the short channel process?
No. Use the models from the project statement. And if you remind me, I'll show you how to do that. It's easy.
Okay.
All right. So let's go do some spicage. let's,
So where does it feed back to the input?
okay, this is one, okay, so if this goes up, what does this node do?
Goes up,
Goes up. What does this node do?
goes down,
And what does this node do?
goes
Down. So if this goes up, this node goes down. So this is the minus input of the op amp, and this is the positive input of the op amp. This is the output of the op amp. Have I put the op amp in a feedback configuration? No, because I'm designing the op amp. Right? Now you're asking, you're designing a chip, which is an op amp chip you're going to use in the lab, and then you're holding the chip going, where's the resistors and the feedback? Well, you haven't added them. You haven't put it in a circuit. You haven't used it. You have to design the op amp first. Okay? So let's go. That doesn't make sense? Yes? No?
Yes.
All right. Let's go over here, and why don't I just do it in this folder? And let's just, whoops, let's go to 24. And let me just pick one configuration. Okay, so I'm going to just use the op amp from the book. Notice that the W here is 5 microns, the W here is 2.5, and if I go into the bias circuit, all the NMOS have a W of 2.5. Okay, so it's exactly what I said. Here I cascoded, but in the paper I didn't cascode, so I'm going to get rid of those just so it's not like, well, wait a sec, you didn't cascode, now you are. What's up with that, dude? We don't like that. Okay. Does anybody know if Co dropped the class?
No, it's still.
To make sure they know I notice they're missing. Whoops. Okay. Looking good? Would it make anybody happy if I did this instead? How about I put this at 2.5 and m equal 2? It's the same thing. How about if I break it into two parts? If I right click on this node, highlight net, there it is. Before I forget, I'm going to say save as, and why don't we, just for the heck of it, go up to our class web page and call this, why don't we call it lecture, what's the lecture today? 23?
22.
It's 22? Alright, give me just one sec.
It's 23 because you got us watch lecture 20 from last year, which was technically 21, so then Tuesday was 22 and today's 23.
Boom! No, you told me lecture 22. Alright, so everybody cool with this? Now I'm going to get out the scissors here and I'm going to get rid of this. And can everybody make a symbol for their op amp? Yeah, it's in the tutorial. Yes. If we have, yeah, we can, if you need me to do it, I'll play the tutorial for you and then, I mean, all right, so what am I going to do now? Source follower. Let's zoom out a little. You know, I don't like this V-bias 4 here, or here, or here, or here. I'm going to draw a wire through there. Boom, to here. And then I'm going to copy this and move it up. Let's move it up here so it looks neat. Now I'm going to get my, see if I had PowerPoint, see how nice it would be. We'd already have this done. And then boom.
So we don't automatically tie if you just drag the wire across
Yep.
all those?
Yep. Whoops, that's not what I want to do. I want to do this. And what's the purpose of the source follower? Tell me in simple language that shows you know what you're talking about. Yeah, so it doesn't load the output of the common source, so I can drive a resistive load without killing the gain. Because if I put a resistor here, the mega ohms that are there are going to be loaded, right? So then let's go and call this V out, and it's going to be an output. And then we'll do this. And then you know what? We'll talk about this other stuff later. I'm going to just show you, because we're not doing rigorous theory right now. We're just showing you something that works. Then we'll do the rigorous theory later. And then let's go and add a couple more. Let's call this VM, and it is a input. And let's call this VP, and it is an input. Control R it. And let's put it like this. Yeah, I remembered at the last minute. And then let's go right here and click on this person here and make this a bidirect, what do we call it? How about input? And then let's drag it up. And let's see, what else can we do here? Okay, so in this op-amp, do I need this elaborate bias circuit? I do. I only have one bias voltage, right? So I could just get away with the beta multiplier and none of this other stuff here, right? I could get rid of all of this except for the beta multiplier. Does everybody see that? Questions? And then I just take this node right here as V bias N or whatever I want to call it, and that would be my output. So if you turn in your projects and you got a bunch of gratuitous circuitry, you're not going to get a good score. Well, I mean, you may still get a good score. I'll just take points off. Okay, any questions? So why don't I, just for the heck of it, I'm going to do the following. Oh, crap. Ugh. You know what I just realized? Oh, no, that's fine. We're using the CMOS EDU models. I was thinking I was going to do it in the C5 process, but that's your project. I don't want to do too much. Okay, so why don't I quickly hit save and then go to, let's see, what is the command? Is it view? No, it's create a new symbol. So this is a schematic. I'm going to create a new symbol, and I'm going to call this symbol, how about lec23 underscore ex1 dot asy. And then why don't I go just draw some things in here. How about, everybody see how I can press line? Wait, I'm doing something wrong here because it shouldn't be this hard. I should be able to hierarchy, create a new, open the sheets, no. And I'm leaving out some step, I don't remember, but it's fine. Okay, so I'm going to use these here to draw a line. And I could just press L, but I'm not going to. I'm going to be sloppy. Boom. You're going to draw better than me, right? No one's going to say, but that's what you drew. Hit escape. Now I'm going to go draw a circle. Oh no, I don't need a circle. I'm not drawing an inverter. Now I'm going to press pin. I'm going to add pin port. And I'm going to call this VM. And I'm going to call it pin justification. I want it to be on the left, I think, and we'll just leave it like that, and I'll say OK. Oh, no, I didn't want it on the left, I want it on the right. Alright, so let's edit that, and we want it on the right. OK. Then I'm going to press L, make a line here, and you're going to be not as sloppy as me, right? Then I'm going to press P again, and then I'm going to do a VP. What does this correspond to? Yep, and then I'll press L and draw a line. So those lines really don't do anything, they're just for us humans. Then I'm going to press P again, and we're going to call this VDD, and we want this on the bottom. There's our VDD line. So again, I don't even need the lines, but it makes me feel good when I have lines in schematics. And then what's the last thing? No, V out, yeah. Yeah, good enough. Alright. Save. Close. So do I need this in here now? Nope. So I'm going to actually go File, let's hit Save, then File, Save As, and then we'll call this Lecture 2. Okay, and then because I'm lazy, I'm going to go boom, boom, and let's get rid of that. And then let's go to add a component, and what component am I going to add? That's right, the op amp I just made. There it is. Yay. Questions? You don't like my symbol? Looks like crap. Alright, so then I move this up, and what's the point of what I'm doing right now? Not rigor, just to show you you can do something. So I'm going to connect my output back to my minus input, like that. Then on my input, I'm going to connect a voltage source. Oh wait, let's connect this to VDD, just to power the op amp. And you know what? And you don't need to show the symbol, so you could get rid of the symbol. I'm going to go back and open that symbol and edit it a little bit. And nope, I don't want that. I want your example here. Don't want you telling me I'm getting lazy with the labels. So I'm going to put a line and go boom, escape, line, escape, line. Everybody like that? Escape. I probably should have put the minus on the bottom and the plus on the top. Oh well. And then I'm going to right click here, none, 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 and none. Do I really need the text there? No, because I know that's minus plus. Okay, close that, looking good. And let's see, I don't forget my dot include, or else I inflict pain on myself. Does everybody feel that, know that? One more time, if things don't work, check to make sure you've included your SPICE models.
So even though you have the dot include in the actual schematic for your symbols, you have to still include it in your...
No, I do not. In fact, I don't want those in there. And I don't want this. Because then I'll get an error because it'll say voltage sources fighting one another. Error, error.
Is that what it sounds like?
It isn't Lost in Space. Will Robinson. Did you get that reference?
Yes.
Okay. Alright, is everybody cool with what I've done here? You know what? I don't like this thing. It's scaring me. I'm going to get rid of it. Boom. Then I'm going to go here and I'm going to go copy. And I'm going to do a Control E. boom, and then we go here. And even though I know how I don't do this for my project, I'm going to add, just to show you, a current source here. But I know I can't do that for my project. So don't say, well, you did that in class, because I'll be like, you can tell I'm damaged. Alright. No monkey see, monkey do. That's bad. What's the bias current then for this process? Yep, 10 microamps. So let's go ahead. Does everybody see how I did? So I don't have that big biasing circuit. But of course, you're going to put a beta multiplier in, right? So everybody understand what I just did. Question?
That was my question.
What?
The one I was asking about.
Oh, okay. Does this look good? No magic? Think it's going to work? Let's go back and grab a voltage source. Let's make sure these are connected just to be safe. Yay. And what's VDD for the C5 process? 5 volts. It says in the top of the models, and I think I even said it in the problem statement. Okay. Oh, whoops, let's just call this 2.5. Looking good?
For your bias,
Yep. Nope. Because in this one I need 2 currents flowing in here. Oh, thank you. That's what I get for copying. Probably would have worked better. Alright, and let's call this node, let's call this VN. Keep hitting the wrong thing. VN, and one more time. VN. Let's move that. And then let's label this VN. Boom. Is everybody cool with that? And then why don't we start out, just to make sure I don't have any issues, with a .op. And I'll hit save and then run. And first thing I'm going to check is what's the current being supplied here. Why can't I get the current that's flowing there? No, it's 48 microamps. Does that seem reasonable? Let's find out. This is where you ask, does somebody know what's going on? It's a trivial question. 1, 2, 3, 4. 4 times 10, well, it's going to be a little bit higher, 40 microamps. Is 48 microamps a reasonable value? Yes. Did you see how easy that was? The other easy question is, what's the power dissipation by the op amp? Oops, you know what I did that's messed up here? That's why it's a little high. This isn't 2.5. Let's put it at 0.5. Because if I put it at 2.5, these turn on and it basically shorts this to this. So let's run the sim again. And then we look. That's 51. That's even higher. But still reasonable. What's the power dissipation of the op amp? Neglect this thing. 1 volt times 51 microamps. How would I estimate it looking at it? Let's see, I got 20, 30, 40, 1 volt. You see how easy it is to estimate the power? You don't think deep there. So when I give you that on a quiz problem, you go, gee, that was easy. Because current source times power supply. Okay. Let's see, this voltage is 0.5. What do I expect the output to be? Well, what is the name of this circuit topology? So voltage follower, what do I expect the output voltage to be? 0.5. It's not going to be exact because gain isn't infinite, but let's find out. Oops. 494. Pretty close. And could we calculate based upon the open loop gain what the value of the op-amp open loop gain is? And if the op-amp open loop gain gets higher, what happens?
It's closer to.
Yeah, so how would I quickly, because I'm learning, and I've got the power of the simulator, how would I quickly increase the op-amp gain? This fundamental question from chapter 9. How do I increase the inherent gain of a transistor? Easy, I don't want to spend time on this. How would I do it? Decrease the current, remember? So let's go to 1 micro, hit save, close, whoops, run. $498.73. I'm learning and I know what I'm doing. Let's go back to 10 because I don't want to have a super slow op-amp. What should I try next? How about let's do a DC sweep to look at both the output swing and the common mode input range of the op-amp. Okay, and before we do that, let's go into here and I want you to tell me what's the minimum output voltage? VDS sat. Everybody see that? Any questions about that? Well, what's the minimum input voltage? Remember, the output's tied back to the input in this particular configuration. What's the minimum input voltage? VGS plus VDS sat. So which one's going to dominate the output swing for linearity? The input common mode. Remember, this output is tied back to here, right? This output is tied back to the minus input. Does everybody follow that? Okay, so which one's going to dominate? What do I expect the minimum output voltage to be? Yeah, VDS sat plus VGS. These start to shut off. Things will become nonlinear. When I plot it, they'll start to deviate. What about the maximum value? What's the maximum output? So the input limits how the output swing for linearity because I can't drive the input below VGS plus VDS sat. Anybody unclear about that? What about the output? How high can the output go? Well, I know this guy can go pretty close to VDD. Does everybody follow that? We derived that last time. But what's the output voltage limited to? Nope, because remember, the largest voltage this can go to is VDD minus VSD sat. But then I have another VSG here. So the maximum this will go to is VDD minus VSD sat minus VGS. So I'm not going to have that large of an output swing. But let's find out. So this topology has issues if I want wide output swing. So let's go close this. Oops. And this was lecture 3. Let's go here, DC sweep. Let's sweep V in from 0 to 1 in 1 millivolt steps. Just as a side note, if you're trying to find the gain of the op-amp and you have a 1 millivolt step, the maximum gain is going to be 1,000 or 1 over 1 millivolt. So if it goes from 0 to 1 in 1 millivolt step and you look at the gain of it, how fast it changes, it'll be 1,000. So this will limit the maximum gain you can actually simulate. Okay, and I'll talk about that more later. Okay, so we hit run, and we plot V in. That looks right. Now we plot V out. Boom. Then we go save, save. Questions? Wait a sec. Down here at right around in here, we start to see the output doesn't start to work. Here we see the output can't get any higher than about half a volt. That makes sense. We have 50 I don't remember what it was, 80 millivolts for VSD sat, and then 250 millivolts with body effect for this, roughly half a volt. The output's not going to go any higher than half a volt below VDD. And that's what I'm seeing. Any questions? Where is the operating range then looking at this?
0.1 to 0.5.
Yeah, right about here to here. Now you have a 1% margin, so you start to see even a lower voltage, it starts to deviate, right? And if you go through the calculations, you'll see that, hey, the diff amp starts to shut off at about 0.3 volts, 0.25 volts, whatever the calculation is. Okay, but I'm going to make things worse. But before I do, does everybody understand that it's a voltage follower? The input should follow the output. Okay, what is the impedance that's presented to the voltage source here? What's the load it has to drive? How much current does VN supply? None. That's the whole point, right? I put this in here. It doesn't have to supply current. However, I don't have a load. So I'm going to go make matters worse. And I'm going to put a load on here. And what's a load? Oops, I already told you. Let's put 50K. Yeah, let's put 10K. Let's call this RL. Looking good? So let's hit run. Let's hit save. Run. Plot V in. Plot V out. That's a little bit too close to what we previously had, so let's put a 1K load on here. Take a picture with your mind's eye where this is rolling off. Run! Oh, now we're killing it. Failure is good. You know, when you design experiments, you need to design experiments so that some fail when you're testing. You always have to have things that fail because you can learn from failures. Questions? Everybody follow? Does it seem magical? Do you feel like, wow, I actually know what's going on? Does it make you feel better about the projects? Cassandra? No? All right. His class is too much work. All right. Let's do another one. Shall we? Let's go in here. And then what I'm going to do is I'm going to take and I'm going to change. First I'm going to save this as a different sim since I don't want you to say I'm ripping you off with simulations. And I'm going to change this to a pulse. And I'm going to give the op amp some time to settle. In other words, I'm going to, okay, so what I mean by that is when you power up the op amp, the DC bias currents and the capacitances have to charge, right? So I don't want to just start the sim and then hit it with a pulse. I want to wait a little while. So here's what I'm going to do. I'm going to hit a pulse. I'm going to start at, say, why don't we go 0.4 and go to 0.5. Let's do a delay of 1 microsecond. Let's do a rise time of 1 nanosecond. Then let's do a fall time of 1 nanosecond. And then let's do an on time of 1 microsecond. And leave it at that. Looking good? And then let's go over here and do a transient. Stop time, let's do 3 microseconds. Time to start saving, let's look at it from the beginning. Maximum step size, 1 nano. Where do I learn about all of these things? Well, like the pulse statement. Chapter 1. Okay, so does everybody see what we got? And I'm going to put this back to 10K so it's not crying. Everybody cool? So let's hit save and then run. And then let's plot V in to make sure it's what I think it is. Is the input voltage correct? Is it within the input voltage, common mode voltage of the op amp and output swing of the op amp? Yeah, does everybody see that? We saw in the previous sims, the output can go easily between 400 and 500 millivolts, if I remember correctly. That was right, right? You know what? That's a little too close. Let's go 350 to 450. Hit run. Boom. Then let's look at the output now. Boom. We see our little offset, which is because of the finite gain. Is everybody cool with that? We see the settling time where it settles before it hits the, wait a sec, it's not going all the way up. Let me try a larger resistor just to make sure there's not an issue there. I haven't done any calculations. I don't know what that can, okay, there we go. And let's blow it up so it looks better. We see the gain. How would I need to increase the gain if I want these to be tighter. I could go back and put 1 microamp in there, but it'll slow everything down. Does everybody see what I'm doing? Does everybody understand what's going on other than why is there a pulse here? How do I minimize this? All that stuff. Questions? What about if I put a capacitor there? Yeah, you can play around. I think I've given you enough. Does everybody see the real op amp? Let's do one more sim just for the heck of it. Yes. File, save as. Example 6. Okay. And then let's go change this to a sine. And then I'm going to put a DC offset of the sine of how about 0.35. I'm going to put an amplitude of 50 millivolts. I'm going to put a frequency of 1 kilohertz. And then no delay, none of this nonsense. So why do I need the 0.35 volts there?
So that there'll be a voltage in your your E minus port.
Yeah, so the input my input signal's in the input common mode range of the op amp. If it's not going to work. Okay? So now I say okay. And then I'm simming for a sine wave of 1K. Notice I'm not using megahertz. So here I'm going to go 3 milliseconds because 1 kilohertz has a period of 1 millisecond. So I'll hit OK. Then I'm going to hit run. Plot V in to make sure that's what I think it is. Oh crap. I left this 1 nano in for some reason. Let's get rid of that. Well, I don't even need that. Okay, whatever. So hit save, run, plot V in. Oh, what if I see a jagged waveform? Yeah, dot options, plot win size equals 0. Now I plot my output. Boom, there it is. Man, I can design an op amp. Of course, I don't know what I'm doing at this point because I haven't talked about how to design it, but I can at least use the stuff I've learned to throw an op amp together. Any questions? Yes?
When we did the pulse, they had the jagged edges on it.
Yep.
Is that, what, like the compensation capacitor?
Yeah, that's from the compensation capacitor. The compensation capacitor has to charge and discharge, so the fast pulse from the diff amp feeds through right to the output. Yeah. Any other questions? I'm going to do one more sim. Does everybody see how I'm careful to ensure the output swing is okay in the input? But you see how the input is off a little bit from the output? The output's not able to pull the input all the way up because of this load. We could put 1,000 ohms there, or a mega ohm, hit run and it would look a little better. Yeah, maybe not. All right, let's do one more sim. Questions? Okay, so here's what I'm going to do. Yes. Let's go and do the following. And again, you probably should put the minus on the bottom. And let's do File, Save As, and let's save this example 7. Save. And then let's go use this op amp as an amplifier. Let's put a resistor in. And that resistor's value I'm going to put as 100K. And I don't like things to overlap like that, so let me pull that up. And let me copy. And I'm going to discuss this because there is a couple of things that we need to know. So your project doesn't require this, but this is, what's the gain of this topology? It's a non-inverting. What's the gain? 2. Remember I told you memorize the 2 inverting and non-inverting. You take your PE, you take your EIT or whatever, FE. Those are always on those, all right? You need to know those without thinking, okay, what the gains are. Okay. So, if I put 0.35 volts DC right here, okay, the gain is 2. What does this become? 0.7. What does this become? 0.35, it's a voltage divider, right? You know what? I hate ugly schematics. There we go. Does everybody follow that? Well, when I do signal processing, I want my analog signal swinging around some common mode voltage. Here, if I run the sim, it's not going to work right because I'm not swinging around a common mode voltage. So let me show you. Let's hit run. There's my input swinging around 350. My output is going to be way up here, kind of saturated, because the output can never go up to 700 millivolts because I've got a common mode voltage that I'm swinging around of 0.35, but here I've got a voltage of ground. So I've got to change this voltage so it's the common mode. So when I put in 0.35, I get 0.35 out. So let me do that real quick. You can play around with this later. I just want to introduce you to this so that you have seen this before, so it's not totally new. This is what's done in just about all chips nowadays, is they don't use ground for the common mode voltage. They use somewhere generally between VDD and ground, VDD over 2 for the common mode voltage. So we'll put this at 0.35 as the common mode. Does everybody follow? So now when this is at 0.35, this will be at 0.35, this will be at 0.35, and how much current flows in the 2 resistors? Nothing. Does everybody follow that? Okay, so let's hit run. Hey, well, we should reduce because we're running into issues with the maximum amplitude because we don't have much output swing. And now we're seeing the offset. But hey, the output is twice as big as the input. Does everybody see that? Because now my common mode voltage is 0.35. Questions? Is that enough examples? Okay, so let's go back now and return to the book and talk about 2-stage op amps. I'm not in our initial discussion because it only makes the circuitry a little bit more complicated. I'm not going to put the output buffer on. So we're only going to be driving capacitive loads. Okay, so we're going to do a couple of things here. Does everybody think we're having a quiz today? I had a quiz last time, but we ran out of time, so we'll definitely have a quiz today. All right. So you just seen this topology. And this is the output of the op-amp. And I want you to tell me if I increase the W of this transistor, I start driving that W up, what happens when these are at the same potential? What happens to the current flowing in this transistor as I increase the W? I goes up. But this is a constant current source, right? So that causes the output to go up, correct? So if I don't size this right, the output starts going up. However, this is VCM. However, when I feed that output, it starts going up. I feed it back here. What does it do? Forces the output to go back down. But hey, it's going to go back down until this current is equal to this, which means this voltage will be above this voltage, which means these two terminals will be at different values. So what I'm doing is I'm forcing there to be an offset in the op-amp. So let me comment on that. When I model offset in an op-amp, I do it the following way. I add a voltage called VOS in series, and it can be plus or minus. It may be due to the mismatch in the transistors that I add right here, and I analyze my circuit with that VOS in there. Okay? Now I want to plot the transfer characteristics of the op-amp, then I want to talk about the slope and the gain. Okay, but does everybody see how if I don't size this right, I'm going to get an inherent or systematic offset? Okay, so I'm going to play around with this now. Before I do, let's do one more plot. If I take a real op-amp, and let's just use the op-amp from the chapter, and I tie this to, and was that op-amp in half micron? I think it was in the, in the nanometer process. Yeah, it was. So this will put at 0.5, and this I'll take and sweep. There's no feedback here, right? There's no, so what I'm going to see if I plot V out, and sometimes people will make a comparator using an op-amp without feedback, right? And I plot V in. When V in is below 0.5, what do I get? When V in is below 0.5, what do I get? This is a trivial question. Okay, so this is my minus terminal. So this is VM, and it's at 0.5. This is my positive terminal, and let's say it's at ground. So this is off. What happens here? Goes up to VDD. What happens here? What happens here? Goes to ground. In fact, it's going to stay at ground until VP gets close to 0.5. Wait, you need to make sure this is really clear in your head. This is below this, the output's at ground. This is above this, the output's at VDD. When they're equal, or nearly equal, the output's some range between 0 and VDD. That's op-amp action. That's why I need feedback. That's how I use this as a comparator to compare two voltages. So below 0.5, I'm going to be here. Above 0.5, I'll be here. In the middle, and I'm going to show you this in Sims in just a second, I'm going to get a transition. This slope is the change in V out with respect to V in. That is the gain. So, remember I made a comment about a 1 millivolt step? If I set my step size to 1 millivolt, what's the maximum gain I can measure when I look at the derivative? 1 volt and 1 millivolt, 1,000. So if you're trying to, why can't I get my gain higher, and your step size is 1 millivolt, you'll never get above 1 millivolt or 1,000. Even if the gain's 1,000,000. That's the slope here, AOL. Now I'm going to show you that. If I have an offset, how do I model offset? No deep thought. I put a voltage source here that I call VOS that models the offset. It shifts the curves this way, one way or another. And you can just look at that as adding the V in to shift the curve one way or another. Questions? So let's do some Sims. And I'm going to follow along with me in the book. This is figure 24.3. Here's my first plot. Notice I'm only sweeping VP from 495 to 505 because I don't need to see all the stuff below where they're not equal, right? That's just going to be 0 in VDD. Oh, but you know I'm learning, so why don't I change this real quick and say, oh, let's go from 0 to 1. Hit run. Now I see that abrupt transition, but it's harder for me to see the gain, but this is exactly what I said. Below 0, I'm at 0. Above 0.5, I'm at 0.5. The derivative of V out is the gain. In this case, it says 440. Let's mess things up. Let's go back here. Actually, let's just reopen it. And let's put a step size of 10 millivolts. Or actually, before we do that, let's just run the sim and see what our gain says. Oh, wait, here the gain was 1,000. When I did that other sim, the gain was 400. Let's mess things up further and make the step size be 2 millivolts. Wow, what the heck's going on? Does everybody see how I stepped it in small two-course increments, so it's not actually tracing the curve? It's going 2 millivolts apart, so the max gain I would get is less than 500. Questions? It's not all the way to 500 because I catch a point right in the middle of the transition. It doesn't go all the way from 0 to 1. Does everybody see that? Okay, so let's go look at the next one. In the next one, I change this PMOS to 50 microamps. Okay? I'm sorry, to 50 microns. So this node has to go way high to shut this off so that it can sink the current that it needs through here. So that means there's going to be an offset on the input of the op-amp. So I'm going to do the sweep again, and I'm going to see the curves change. So let's see what happens. Now, instead of switching at 500 millivolts, they move to the left, and that's my offset. I've introduced that on purpose because I made that NMOS or that PMOS too strong. What if I make this PMOS too weak? What if I go and make it Let's go show what happens when I make it 5, which is the right size. Hit run. We get the curve we had before. And then what happens if I make it weak? Let's say I go to 0.5. What do you think is going to happen to the offset? It's going to move the other direction, which I haven't even simmed far enough out to show it. Let's go to 515. Does everybody see that? I normally don't design for that. I normally design like I've been taught to have more, to have everything biased up correctly, but I may need this to be bigger. And if I want it to be bigger, say 50 microns, oops, while at the same time I don't want an offset, then I have to increase the width of these as well. And what's the drawback of that? Burn more current, burn more power. Oh, there we go, right back at 500. Okay, I want to pause here, so when we come back on, I want to do one more example before we take the quiz, but when we come back on Tuesday, it would be really good if you read the book, because we're going to talk about compensation and how to select that C sub C. That's a big part of the op-amp design. Okay, so let me do one more example. And before I do that, notice that that offset we just went over was because I didn't size the transistors correctly, but it could be because of mismatch in the transistors, and commonly that's what it's more often, the mismatch. So I want to do an example using offset, and I've done it already, but I want to do it one more time, because now you're saying, hey, I actually know how to design an op-amp, and I know what the offset is. I want you to do an example of the offset in your projects. So say you design, now offset is something you subtract out of the accuracy. So sometimes you can't get rid of it, all right? If you play games fiddling with the device sizes so the sim looks good, that's not good design. Okay, so if I say your V offset is plus or minus 20 millivolts, estimate V out for your design. And I'm going to assume AOL is infinite. And so here's your design. So how do I estimate V out? Okay, first thing, I've said this numerous times, but let me say it one more time. When you talk about offset, first thing you do is put the offset voltage in series with the non-inverting terminal of the op-amp. So I go, oh, I got a voltage here of plus or minus 20 millivolts. That means this voltage here is V in plus or minus 20 millivolts. And with infinite gain, that means V out is equal to V in plus or minus 20 millivolts. So if the offset's random, that random offset is going to cause my output to change. Let's do one more. Got that Rihanna song "Work" stuck in my brain. Yeah, yeah, yeah. All right. Did anybody know that reference? One person? All right. No? All right. That's a good song. How do I solve for V out here? Then I go, boom, circuits knowledge, superposition. V out equals minus RF over RI times V in plus or minus VOS times Oh, with superposition, that's grounded, times 1 plus RF over RI, because I know the two topologies. I know the gain of the inverting when that's zeroed out, and then when that's there, I zero this out, and it's nothing more than the non-inverting topology. I write the answer down, or I can derive it if I have to. There's where we go. No other questions? Does everybody follow? And what are you going to do by Tuesday besides work on your homework? Read the book so you know what compensation is. So when I'm going over it, it's not me being Charlie Brown's teacher. Womp, 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 womp. All right, let's take our quiz.